We are pleased to have you here for our next in the series of webinars on frontier of big data, artificial intelligence, and analytics, where our goal is to unleash the ideas and insights for harnessing the successful future of business and society. The seminar is co-organized with Tomohiro Ando, Melbourne Business School, University of Melbourne, Robert Cohn from University of New South Wales Business School and School of Economics, and myself, Valentin Zeleniuk, from the School of Economics of the University of Queensland. And before moving forward, I would like to give an acknowledgement that our university, University of Queensland and University of Melbourne, is happy to remind that in the spirit of reconciliation, we acknowledge the traditional owners of country throughout Australia and recognize their continuing connection to land, waters, and culture. We pay our respect to their elders, past, present, and emerging. A little bit on the housekeeping rules. The structure is presentation is roughly about 30 minutes. We are flexible. It could go a little longer depending on how the speaker feels. The target is the 30 minutes. Then we'll have a discussion, questions and answers. We'll have already a few questions that were submitted from the audience. And if you have any questions that you think would be interesting for you to hear and for others, please submit them through the Q&A. And then you will have also the option to vote. And the more people vote, the higher the question will go. And then because the time is limited, we will choose the ones from the top of the question list that received the highest number of votes. Now, today it's a special pleasure to have Professor Michael Littman, Royce Family Professor of Teaching Excellence and Professor of Computer Science at Brown University, who will tell us about telling, inspiring, demonstrating, and explaining, and getting machines to do what we want. This is wonderful because if we have ever the rise of the machines, we know who to contact to tell the machines what to do. Now, we'll see Professor Littman in a moment. Few interesting facts. You, of course, you can and probably already Googled and have seen a lot of interesting information about Professor Littman, who is one of the leaders in the field of machine learning. I will just mention two facts, which you can also find in the as I understand, his website called litmania.com. The two facts is that let me start with this one, is that his Erdős and Bacon numbers, both 3, so the joint one is the number 6. For those who know, they know that that's pretty good. And even more unique fun fact is that he was one of the very few, to be precise, one of only 4 in the world who were singing in the very first attachment that was sent in the 1992, in the good old days. So that's very interesting. So you can see that he was indeed at the very beginning of this field, or at the very important stage, and is currently a leader in this field. So we're really pleased to have him here. Professor Littman, the floor is yours.
Many thanks. Wow, that was a fun intro. I haven't had pictures that are almost, what is it, 30 years older? pictures of me from 30 years ago. So that's, yeah, that's very disturbing. But it does, it does kind of provide a perspective on sort of where I'm coming from. So I've been in computing. I guess I started when I wasn't really part of the community then, but when I was 13 is when I first started to kind of get involved with computer science. And very, very much from the beginning, I was very drawn to this notion of artificial intelligence and trying to create systems that are, smarter than computers, which are very literal, or at least traditionally have been very literal, very dumb, but also very powerful, right? So if you think about what a computer can do for us as individuals, is it can help really amplify our ability to get things done. And so at the moment, people who are programmers know this quite well, right? So if you're a programmer and you've got some particular like filing task or something that you need to do, or you want to create a website or something like that, like it's not that big a deal. It's a thing that you can do. You can just express to the computer what you want it to do, and it'll do it on your behalf. And it's a kind of force multiplier, right? It's ideally, or in a sense, what the computer is doing is what another person could do if you could just get another person to do it for you. So the computers are very taskable, right? And so we all have things that we need to accomplish and need to get done. And those of us who actually can task computers with the things that we want done can be much more productive, right? And so this is something that I believe in the limit, or in the not so distant future, is something that really should be available to everyone, right? We should all be programmers in a sense. And one of the reasons that I'm so excited about artificial intelligence, and especially the recent developments over the last, 5 years, things have really exploded in interest, is that it holds the promise for making it easier for us to tell machines what to do, like all of us, right? Each of us to get our own thing done. At the moment, that's not really what we've got. And in fact, one of the worries that I have is that computation for many people is being used as a way of kind of controlling us, like getting us to do things, providing us a service, but in exchange, taking our data, right? So the companies that are providing these super useful products to us, these software products to us, a lot of them are also, they're kind of bargaining with us, and they're saying, if you give us your data, then we'll give you these cool tools. We'll give you email. We'll give you cool web search. We'll give you, photo systems that transform your look in various ways. And it's neat, but we're really letting them have all the power. And I think that's not how computing was originally envisioned, and it's not really what it could be. What it could be is, if you want something done, you tell the machine to do it and it does it for you, right? You can have a lot more power and control in this relationship with machines. And so I want to kind of give a little update on computing and artificial intelligence from that perspective, right? So there's a lot of debate, there's a lot of discussion about the impacts that AI is having on the world. This is a different take on it. This is a take that says, if we do this right, AI can it can really empower all of us. It can make it easier for us to get things done with the help of machines. So let me focus on that as a topic. I find it useful to, I don't know, I'm a bit of a psychology groupie. Like, I love psychology research. I'm not a psychologist, but I tend to think very much that way. And so one thing that's really useful, the way that cognitive scientists think about, say, animals like cats and the way that they interact with the world, is that, there's the cat and there's the world, and they're interacting in the sense that the animal's taking in information about the world through its sense organs, its eyes, its nose, its ability to feel, and then it's acting on the world by moving, jumping, meowing, eating, biting, the different things that cats can do. And it has computationally, if you will, a kind, or at least this is the way that people think about cognition these days, is as a computational metaphor, that somewhere in the animal, there's something kind of like a program that says, okay, well, I'm trying to eat a mouse. When the mouse distance is greater than my pounce range, I'm going to wait. But if it ever gets close enough, then I'm going to pounce. Okay. Now, that same kind of way of looking at the world holds also for robots and other computational agents. So for example, if you've got a robot arm on wheels, it might need to do something like, okay, it needs to pick up a block, If that block distance is greater than the gripper range, then it needs to move closer to the block, right? So it's a little control program that lives inside the robot and tells the robot what to do. So if you want to task a robot with things, could you please help me bring in the groceries, something like that, you have to somehow express to the robot that goal. And at the moment, writing programs is really the only way that we have to do that. All right, so that's the notion of delegation, right? We have some thought, like we would like a cleaner workspace. We want to tidy up the house or something like that. We have to somehow delegate that, convey that to the machine so that it actually gets done. And I don't know, as maybe a helpful example, let's see, I don't know, would you be able to hear this, or do I have to share it differently? Let me try to play this little video. It's quite short.
Hi, I'm Ashley.
Did you hear her? Her name is Ashley? Okay, all right, so this is Ashley.
We can hear.
Okay, good.
Hi, I'm Ashley, and today I'm going to show you how to water your tomato plant. The easiest way to determine if it needs watered is the finger test. Simply stick your index finger about an inch down into the soil. If you bring it out and it's dry, it needs watered.
All right, so what's going on here, I say, to a first approximation, is we've got a task that we want done. In this case, growing tomatoes, which is a perfectly reasonable task. In fact, they're kind of good for you. So it would be great if we could grow tomatoes effectively, and each of us might want to do that. Google's not going to do that for us, right? This is something that we'd have to do ourselves. So yeah, good to grow tomatoes, but caring for them is kind of hard and time consuming. So you got to worry about things like, when do I water my tomatoes? So if we could delegate this to a computational system, then maybe we can get the best of both worlds, right? Our tomatoes growing for us, we get to eat them, and we don't have to do all the work ourselves. So how do we get that across? Now, in the case of this video, she was teaching another person, right? So she was giving some information to us that we can then kind of run on our own processors to make things work. And it reminds me of like the different ways of actually conveying things to people. Reminds me of this saying from William Arthur Ward: a mediocre teacher tells, a good teacher explains, a superior teacher demonstrates, and the great teacher inspires. And so basically they're hinting at 4 different ways of trying to convey information to people. But I think these are actually really great stand-ins for the 4 different ways we have of telling machines what to do. And I really like this, except for the kind of the judginess of it. Like, it's kind of judgy. It's like, oh, well, if you're telling, then you're mediocre. And if you're great, then you inspire. But the fact of the matter is, all of these are really useful. So the great teacher that only inspires but doesn't tell you anything is actually not that great a teacher, right? What you really need is the combination of all these working together to convey the right kind of information to other people. And I think that's where we need to go with machines as well. So let me kind of break down these 4 different ways of conveying, or at least how I see them translated into something computational. So I think of it as a 2x2 grid, because I don't know, I'm a scientist, so I think of everything as 2x2 grids. So there's 2 different dimensions that I want to mention. One is, how are we conveying the information? Is it in the form of instructions, like do this, do this, do this? Or is it in the form of incentives, right? I'm not going to tell you specifically what to do, but I'm going to reward you if you do this sort of thing, and maybe punish you if you do this other sort of thing. People are very sensitive to incentives. It's a really good way of getting people to behave a certain way, but it's different. It's distinct from actually just giving instructions. Then on the other dimension, we can actually think about how we're giving these instructions or incentives. We can do them explicitly, like, here's your incentive. You just write them down, or you can convey them through examples, right? Through actual examples of behavior. And so each of those combinations of instruction versus incentive and explicit versus example creates one of these tell, explain, demonstrate, inspire combinations. And from a computer science perspective, telling is traditional programming, explaining is reinforcement learning, demonstrating is supervised machine learning, and inspiring is, I don't know, I'll call it loss function learning. So let me kind of tick off each of these to give you a sense of what I really mean. All right, so if we're automating watering tomatoes, and we're going to do it using the tell mechanism, right, by actually just writing a computer program, we need to consider, well, what are the different actions that we have available? What can the machine do? So if we have an automated water sprayer that actually has information about moisture, and it has information about the time of day and maybe the sunniness, whether it's rained, we can then program it. We can actually send it commands, so send it actions with a little bit of control flow. So the actions might be, well, I want to spray the water I'm spray the water today. Or it might be, I'm not going to spray the water today. This is a very simplified setting. The sensing, it could sense what the rainfall has been, whether it's sprayed recently, what the temperature is might be useful, the height of the tomato plant at the moment. All these things might come into the decision about whether to spray on a given day. And we connect a computer to the sprayer, and then we program the computer. So that's the setup. And I'm going to talk about this, each of the different styles of telling a machine what to do in that context. So the telling mechanism, or traditional programming, is give the computer explicit instructions for what actions to take in what circumstances. And the key idea that makes this work is something called control flow. That there's the commands and the sensors that are specific to this task, but they're kind of interspersed with control information, right? Telling it when it should do those and how it should do those and how many times it should do those. So we might have a program that looks something like this. So in the bottom corner there, you see it says forever. In other words, we have this kind of looping construct that says, I'm going to do this over and over again. The first command says spray today. All right, so it does a spray and then waits for the end of the day. And then the next day, it proceeds to the next command, which says wait a day, so skip today. So this is just a tiny little simple program that just says water your tomatoes every other day, right? It tells the machine to water the tomatoes every other day. It's completely unconditional, right? It's not taking anything into consideration, but it does have some structure, right? It is kind of alternating between spraying one day and not spraying another day. But we can do more sophisticated things. So maybe on each day, so there's a forever loop around it, we'll do a test. We'll say, well, if it didn't rain and we didn't spray, then we should spray today. Otherwise, we can skip today, right? So this is a more sophisticated control structure, but it actually allows for more nuanced treatment of the tomatoes, right? It doesn't just spray it every day no matter what. It waits to see when things are kind of getting dry. So this is kind of the power of programming, right? We can actually tell the machine to mull over the different conditions and then do it the right way. But we had to come up, in this case, I had to come up with this particular structure. Is that the best strategy for watering tomatoes? Not according to Ashley's video, but it's still not a bad one. It's still pretty good. All right, there's other things we could do. I won't go through this program in detail, but stepping up from the notions that I talked about so far, you could actually write your own little program that does a kind of scoring, like how wet has it been over recent days, and depending on the wetness, I'll decide to spray. That logic, that more sophisticated strategy can be encoded as a program. There's lots of different programming languages in the world where you can express these sorts of things, all the way from Algol to Scala. There's visual interfaces to programming that make it a little more friendly looking. So this is a little spraying program written in a language called Scratch, where you just kind of click blocks together. It doesn't have to look cryptic and codey. Sometimes it can look a little more, colorful and friendly. But it's still programming. It's still the idea is you have to work out what the specific steps are and how they should get executed. There's also some things, user-friendly schemes like trigger action programming. As if I play with this a lot. It's a website called if this then that, where you can actually write these very simple little trigger action programs. If this happens, then do this. So I have one that says, if a new weight arrives from my bathroom scale, then write it into a Google spreadsheet so I can keep track of my weight over time, just to be cognizant. So it's becoming easier to write little programs that interact with the world. It's not been set up for tomatoes yet, but it's something that, at least in principle, could be done. But an interesting thing about programming is that it is actually kind of hard. And so one classic example of this that I really like is researchers, I think it was back in the 80s. I think this was done on college students at the college where I was when I was in college. But I didn't participate in this experiment as far as I know. So they asked beginning programmers, so new students in a computer science class, like halfway through the class, so they knew how to write programs. Write a program that will compute the average of a list of numbers terminated by the number 99999. So basically, just keep a running information about they described it in terms of rainfall. That's why it's called the rainfall problem. So I want you to compute the average rainfall, but when I say 99999, that's the end of the list, and then tell me the average. 86% of the students couldn't do it. They wrote a program, it was wrong. Whatever the opposite of that is, 13, 14. I can't subtract. Sorry, 14% of the people could do it, but that's not a great average, right? This is already looking at people who've been trained in programming, and still only 14% of them could do it. Professional developers can do it, and they're much better at programming, but they still have created bugs in complicated systems that have done things like crash spacecrafts, crash cars, crash power grids, crash the internet, right? It is not trivial to write this kind of code so that it works effectively. Even trigger action programming can be hard. So we did some research and determined that 60% of users, they could write programs, trigger action programs that involve conjunctions, like turn off the light if it's after 6 p.m. and there's no motion in the room. But they didn't understand what they wrote. And when we asked them, well, what would this do in this circumstance, they would get the wrong answer. So this is hard. This is just a hard thing. So maybe we need a different way of conveying what we want to machines. And so here's an alternative. This is called, we call it reinforcement learning, but I'll call it explain here. Where instead of telling the system step by step what it should do, we're going to explain what it is that we want it to have accomplished and let it work the details out itself, right? So all we have to do is relay to the computer what's good and what's bad, and then it can figure out the program on its own. So the key idea to make this work is the notion of an objective function. We have to actually tell it what's good and what's bad. We don't have to write programs that say, you know, do this, but we do have to write programs that say, this is good, this is bad. And then it becomes the computer's job to actually select actions to maximize the objective we define. So the objective can just be like, you know, thumbs up, thumbs down, but it could also be like, this is worth 10 points, this is worth 2 points, this is worth -3 points. So we have to kind of make that scoring function up, but then the computer's job is to try to behave in a way that causes scores to be high. And this has been extremely successful in the context of writing computer programs to play games. So back in the day, we used to write computer programs to play games by encoding the rules, like writing programs that did it. And that's just not what we do anymore. The best programs that have ever been created do things based on, well, at the moment, using machine learning. So using reinforcement learning, where you say, well, what's the objective? Win the game, right? And it can detect that for a game like Go or chess or shogi. And then you could just let it play the game for a really, really long time until it works out a strategy on its own. And what's remarkable is these strategies are better than the best human beings to ever play these games. So it really is a powerful approach. You can do not just board games where we know the rules in advance, but you can actually get computers to play video games where what they're given as input is the screen. We don't tell them the rules. We just let them play and try to maximize their points. And boy, son of a gun, they can actually do that in a whole range of, well, in this case, 1980s era video games. There are people have applied them to more modern video games as well. But the 80s games, I don't know. For me, that was very satisfying because these are the games I played as a kid. So in the case of the tomato watering, the way that you might express this, there aren't any programs that do this at the moment, but you could try to think of this as a reinforcement learning problem. And it might look something like this. You tell the computer, all right, you have use, you can sense the rainfall, the temperature, whether or not there's been spray, and the height. And I'm not gonna tell you what those mean, but you have access to those numbers. And you get to choose to either spray or not spray on each day. But at the end of the day, what I want you to maximize is the height of the tomato plant, right? So that's a proxy for how healthy the tomato plant is. And that would be the program that you'd write to water tomatoes. You don't have to pick the strategy, but you have to tell it what it's trying to do and what it can measure to control its own behavior. So that would be pretty slick. Now, the problem is at the moment that the programs that we have for doing reinforcement learning require lots and lots and lots of experience. So you'd actually have to write this program and then wait 10 years, 100 years until it learns a really good strategy. So it doesn't just start happening overnight because it doesn't understand the connection between things like temperature and whether or not that will cause the tomatoes to grow. It has to experiment in the real world. So we use machine learning to do that, right? It actually has to experiment to learn in the tomato watering space. And so here's another example that I particularly like because of how badly it goes, actually. This is a video game called Coast Runner, in which you're supposed to control this little white boat. Hopefully you can see the animation somewhat smoothly on your end, but you're going around a racetrack and you're trying to beat the other boats. But to make it a little more interesting, there's certain things that you can see as the boat crashes through those little markers. In some case, it gets extra points. So there's little bonuses along the way just to keep it, spice things up a little bit. So what you're trying to do is win the game, but you might as well get as many points. You get a lot of points for winning, but you get additional points for things that you encounter along the way. And one thing that's really interesting in this example is that when you apply reinforcement learning to solve this, it does really, really well, but it also does really, really terribly. So this is a reinforcement learning trained boat playing this video game. What you could see is it's, first of all, it's not even playing. It's not even going in the race. It bumbled its way into a cove, a separate part of the game. And now what it's doing is it's rapidly just spinning in circles. And the circles are set up so that it's crashing, it's catching on fire, but it's getting these turbo points. It's getting these extra points. And it's getting points at a faster rate than it would by just going around the track and trying to win the game. All right. So even though the reinforcement learning has kind of mastered this game, it mastered it in a way that's completely distinct from what we really wanted, which was a boat that was good at racing. Instead, we found a boat that's good at crashing into other boats and picking up extra points along the way. So what's the problem here? Like, do we blame the reinforcement learner? Do we blame ourselves for picking a bad scoring function? Maybe. It's an interesting thing that comes up that's not part of traditional programming. Like, it's a different kind of bug that you can introduce into a program that has to do with maybe misaligned incentives, right? We created a scoring function and it just doesn't match what we actually wanted it to maximize. And so this is a whole new category of bugs that we have to worry about. Now, possibly as a good thing, maybe possibly as a bad thing, there haven't been as many fielded examples of reinforcement learning as there have been of other kinds of techniques. But there are some. The Nest thermostat, for example, learns how to more effectively use the heating resources in your home. So it has as a target that it's trying to keep your home in a particular range that you set, but it's trying to figure out how to run the heater at least often, like using the least amount of energy to accomplish that goal. And my understanding is that behind the scenes, it's actually doing little experiments with your heating system to try to figure out how it works, and then using that information to more effectively heat your home. That's pretty slick. Another one is recommendations online. So things like YouTube recommendations. It has a reinforcement learning proxy, which is I want to maximize the amount of time that people are watching videos. I want to make recommendations. A new person comes to the site and says, I would like to watch a video. And the system says, hey, how about this video? What it's trying to do is to get you to basically be on the site as long as possible. So it's learning what kind of person should get what kind of recommendation to maximize this metric. But the thing is that this is kind of bad because YouTube recommendations have been shown to cause people to have extreme political views. So, but that kind of works, right? It's another example of this boat situation, right? Where we told it to maximize something. It seemed like a reasonable thing. It actually went about maximizing it. It turned out not to be a reasonable thing. And we don't really have a science at the moment of how to avoid these negative outcomes. We just have to be aware of them and then fix things when they break. So sometimes it's really hard to know how it's going to accomplish its goal, and it may not be a way that you want. All right, so I want to move on to a third way that's being used a lot these days to program computers or to tell computers to do what we want, and that's what I would call demonstrate, which is supervised learning. So the idea in supervised learning is that we still want the system to learn instructions. We want it to learn to do something. We just don't want to have to specify the conditions under which it does it. And so what we can do is, instead of spelling that out painstakingly, we can give it lots of examples of how we want it to behave. Like, when you see this sort of thing, do this. When you see this sort of thing, do this. We're not telling it what to learn from those examples. We're just telling it what it should do in all these different circumstances. And these algorithms sometimes require tens of thousands, hundreds of thousands, millions of examples, but then they work out on their own they fill in the blanks, or they figure out how to behave. We still use this idea of objective functions, but now the objective functions are actually part of the learning. So what the system is trying to do is maximize how correct it is, right? How well its way of classifying examples matches what your examples said they should happen in those cases. And so the key idea here is data. The key idea is that we're going to program the computer by giving it lots and lots of examples, lots and lots of data. And so in the context of the tomato watering, that would be like mimicking an expert. So we give it a bunch of examples of, okay, there was rain, we hadn't sprayed, the temperature is high, the tomato plant is short. And what an expert says is, in this situation, you just wait, don't water. But another day, there was no rainfall, the temperature is low, but the tomato plant was short, we hadn't sprayed, and so now you should spray. And so we just have to populate this table with lots and lots of examples, usually by just measuring what people actually do, right? It's not a specific act that you have to do. You just have to collect the data of you really behaving in the world. And then at the end of the day, it tries to learn a rule. It tries to learn some kind of way of mapping the sensor information to the action that that the person would do in that case. This is being used all over the place in computation. So spam filtering, the decision about should this this email that you got be shown or should it be dropped into your spam file, that rule is learned through machine learning, through supervised learning. Learning to recognize individual faces or objects in the world, like, for example, these are all successfully recognized by computer. Like the computer's shown the picture, and then it says, I say strawberry, and it's shown another picture, it says, I say backpack. And the way that it came to do that, even though it's never seen that individual picture before, is that it saw thousands and thousands of other examples, and it kind of built an internal rule that actually is better than any human rule for classifying images. It's being used in speech recognition. The reason we can talk to our phones now and they mostly understand us is because of this kind of supervised machine learning. We're translating between languages. Computers are sometimes discovering cats on the internet because there's pictures of cats on the internet. These are all examples where supervised learning algorithm is being used to make sense out of data. The problem with this, just everything's got its own little problem. So the problem with this particular way of building programs is that it can sometimes generalize about the way that the data was collected instead of about the thing that you actually want it to learn. And so a really beautiful example of this is researchers trained a machine learning system to distinguish husky dogs from wolves. They look pretty similar. Like it takes a little while before you can learn, oh wait, no, yeah, that's a wolf. That looks definitely different from the husky. But huskies are very wolf-looking dogs, right? And so they trained a recognizer to distinguish them, and it was getting 90% accuracy, 95% accuracy. It was really good. But then the researchers said, okay, how is it doing this? Let's blot out different pieces of the image and see what causes it to change its recognition. And what they discovered is that if the background has snow in it, then the algorithm is going to say it's a wolf. Now, the snow is not relevant to that, right? But it's a common enough connection in the training data that, a lot of wolves are outside, and mostly because you don't want wolves in your house. So the wolves are all outside, but outside in the snow, and the huskies are pets, and they're in homes. And so you see a lot fewer pictures of huskies in snow. You see a lot more pictures of wolves in snow. So if the algorithm sees, for example, this is a husky, and there's snow in the background, it's like, oh yeah, that's a wolf. All right, so it actually doesn't learn what we wanted it to learn because we couldn't tell it what we wanted it to learn. The only channel we had to convey our wishes to it was through examples, and the examples had this kind of quirk in it, right? A reasonable quirk, but a quirk that the algorithm itself struggled with and ultimately produced an incorrect answer. So, that's not ideal. And we still have a long way to go in helping to kind of bridge that gap so that the rules that are learned really do pay attention to what we want it to pay attention to and not spurious associations. Some of these spurious associations are really problems. Like, so for example, systems that are learning to recommend here's the input is a job application and the output is, should we interview this person? And sometimes systems will learn things like, oh, well, in the past, you don't seem to hire a lot of women. So I can figure out from this resume that's a woman, you probably wouldn't hire them. So, don't hire this person. And that's not the rule that we wanted it to learn, right? We wanted it to learn to interview the most promising people and not just imitate our mistakes of the past. So this is still really hard. I'll very briefly talk about this, this fourth quadrant of my picture, inspiring. The idea is using examples to learn what the incentives ought to be. And the key idea here is counterfactual. So I don't think I have a lot of time left to talk about that. Yeah, I'll have a minute or two. So, so here's, I think this is kind of a fun and interesting example and a little challenge to all of you. So imagine that we've got this scenario. We've got a robot and we want it to carry out a particular task. And we don't even know, like we could do it by a program. We could write a program, but that could be really complicated. We could try to do it by setting the rewards, but we don't know exactly what rewards to set. And if we set them badly, then unexpected things are going to happen. We could do it by supervised learning and just give it lots of examples and have it try to learn the rule from that. But what if we actually gave it examples and had it learn the incentives? Like, what is it that this agent is inspired to do? And so, so here's a concrete example. So we're looking kind of down at an environment with different colored squares on the ground, and we have a robot, and we navigate the robot in a particular way. Okay, so this is what the robot's doing. And now, you know, I want you to think about it. Like, what do you think this robot is trying to optimize? How much does it value, for example, the white squares, being in a white square? How much does it value being in a green square? How much does it value being in a blue square? How much does it value being in an orange square or a yellow square? And so even from this one example, you can actually infer an awful lot. The white squares seem kind of innocuous. The green square seems super attractive, right? The robot seemed to like go all the way across the grid to get to this green square. It looks like it dodged the blue squares. So maybe the blue squares are kind of not great. Maybe they're negative. It couldn't get through that. There's no way to get to green without going through the orange. So the orange might not be great. Like, it doesn't spend a lot of time in orange, and it could, right? It could have driven all the way around it, like all the way through it, but it just kind of skims through it. So it's probably not as bad as green is good. And then the yellow, it must not be very much of a disincentive because it could have skipped it, but it didn't. So we can actually assign values to each of these just based on this one example. And actually these numbers came from a program that we wrote to try to do this kind of inference. So this is a really kind of cool idea, right? We can get the benefits of reinforcement learning, of being, not having to spell out the specific steps without also having to specify the, you know, this price list, that it can be inferred automatically from incentives or from examples. And this isn't being used very much in the world yet, though there is a trick that's being used to generate photographs, artificial photographs, that actually does use something like this internally. So this is a picture that's, right, it looks like a photograph of a woman with glasses, but this never, there is no such woman. This is not a real person. This was generated by a program to look like a picture of a person. And the way that the way that the people who created this system made this happen is they gave it a whole lot of pictures of faces, like actual photographs of actual people. And then they said, try to figure out what it is about these images that makes these faces and these other random, you know, collections of pixels not faces. Like, learn to distinguish faces from not faces based on our examples, based on, we're going to tell you these are pictures of faces. And, you know, the freaky thing is that, you know, you can look really closely. She's got like individual hairs in her eyebrow. You can see her hair's parted in a particular place. She's got nice clean teeth. It looks like a photograph, but there are some weirdnesses to it. Like, if you look in the background doesn't make any sense. So there's still, typically these systems still have little artifacts that you can tell that they're not real, but they're getting better. And it's really scary because at some point these are going to create photographs and we're going to be like, yeah, that really happened. But even if it didn't. So if you want to play with these and learn how to distinguish the fake from the real, there's a site called thispersondoesnotexist.com, and you can have it generate lots and lots of fake faces and some real faces, and you can learn what distinguishes them. All right, so that's my whole pitch. I told you about these 4 different combinations of instructions versus incentives, explicit versus example. Each of them had an element that we added to the idea of programming to make it richer and make it easier for us to tell the machines what to do. But they all have kind of complementary strengths and weaknesses. So, like, programming does what it's told, and that's good because it does what it's told, but it's bad because it does what it's told. And if we told it to do the wrong thing, it will do the wrong thing. Reinforcement learning is really great because it can surprise us, but it's also really terrible because it can surprise us, right? So it's kind of, again, double-edged sword. Supervised learning, it mimics what it's given, which is great because we give it what we want it to copy. But on the other hand, sometimes we give it what we don't want it to copy, and it mimics that too. And Yeah. So I think really the way that we is this, what's hard about this? What's hard about this is it's actually very difficult to say out loud, to write down what it is that you want to have happen. And it's hard when we do it with people too. But the way we get by, and if we rewatch the tomato example from the beginning, Ashley is actually giving us elements from each of these boxes, right? She tells us what's supposed to happen. Like this soil is supposed to be damp. And it's not, so that's bad. So she gives us an objective. She also gives us steps, like take your finger, put it into the thing, right? So that's just an instruction to follow. She gives an example. She's like, look at this soil. This is how it looks when it's dry. And through the combination of different sources of information, she conveys something that's very complicated to us in a very simple way. Ultimately, this is what we need to be able to do with our machines as well. And so this is, I think, what we want to be striving for. All right, so that was my talk. Thank you very much for listening. I did want to just put in one more plug at the end of this. If you're interested in AI more generally and what is the state of AI, how is it impacting our economy, how is it impacting jobs, how is it impacting healthcare, I had the great honor of getting to chair the AI 100 panel. So this is a group that is convened once every 5 years to talk about what is the state of AI today, what are the positives, what are the negatives, where's this going? And our report came out last month. And yeah, I'm very proud of it. I had 17 members of my panel, experts on all kinds of different topics in AI, from specific technical issues to sort of general societal implications of artificial intelligence. And yeah, I just welcome you to go and check it out at the website. There's a lot of really fun stuff there.
Thank you very much, Michael. Thank you. So perfect timing. And now we move into the questions and answers session. So let me share my screen.
Not anymore.
Okay. Can you see my screen?
Yeah, I think we can all see it.
Okay, good.
We certainly can.
All right. So thank you for a wonderful presentation. It's I think the audience who had a chance to look at our previous presentations, whether live or recorded, noticed that it's yet another very interesting presentation that is different from others that we had. And I'm very, very pleased myself about this, because I'm an economist, econometrician, and interested in machine learning, and so far mostly was doing it from statistical perspective or econometrics perspective. And what we've seen is computer scientists like today. We also had before also from computer scientists and from statisticians, and it's really interesting, from practitioners. Very interesting to see this perspective. So some of the questions are also in our audience. We have also more statisticians or more econometricians. So this question, for example, it came from a student who is a econometrician, and question is that in your opinion, what are the three greatest discoveries of the machine learning research?
Yeah. So sure. Thanks. Thanks for asking. So I would let me break it down. I'm going to give two sets of three. So the first three are going to be just, in the history of machine learning. And so to me, the number one thing is just that you can do this at all, right? That we can think of this very deep and ancient problem of inferring from data facts about the world, right? Information that's actually relevant to decision making. Plato and Aristotle talked about this sort of question, like what can you learn about the world, and what do you need to actually make it happen? We've now understood this to the level that we can actually automate it. We can convey to the machine. We can tell the machines that we want it to do this thing, and they can do it. That's that's amazing, right? It took a while to kind of get to wrap our heads around this and figure out what it means and what the issues are. But that to me is just phenomenal. Now, sub things that we figured out within machine learning are, well, for one thing, the algorithms, right? So things like gradient descent, things like decision tree learners, right? There's lots of actual procedures that are extremely effective at solving problems. And so the fact that we've got a bunch of these under our belts now is great, right? So that's another great discovery. If I had to pick one of the algorithms, I mean, certainly the one at the moment that's has the most oxygen behind it is gradient descent, right? The sort of idea that we can train networks of simple computational units using calculus, right? Using the ideas from calculus to set the weights and actually compute complicated things is kind of amazing. So I definitely would put that as one of my favorites there. And then, you know, my own field of reinforcement learning, the idea of temporal difference learning, right? The idea that we can say, okay, we can actually learn about how things are changing over time in a way that allows us to, or allows the machine to make better smart decisions, like more often make smart decisions than dumb decisions. That's pretty amazing. It's amazing enough that the whole notion of temporal difference learning and reinforcement learning, like we stole that word from the psychologists, right? They were already using it to mean something that causes behavior to get stronger, hence reinforcement, right? But we stole it from them and we didn't really understand it. So the computer scientists, the machine learning people thought that it meant reward maximization because that just made a lot more sense to us. It was a more clear goal than just like action strengthening. And now the psychologists have stolen the term back from us in its broken form. And so now psychologists talk about reinforcement learning the way computer scientists talk about, because it turns out that we actually understood the concept in a really powerful way that is powerful enough that, yeah, they're finding evidence of exactly these algorithms in the brains of animals and people, right? People and animals seem to process information in a similar way. So that's a really great discovery. So I could just end there, but you might be asking something a little different, which is, what's new? Like, what are some recent excitement? And so in the AI 100 report, which I already plugged, we highlight 3 that we're particularly excited about. One is the notion of generative adversarial networks. That's the idea that actually generated that photograph-looking image that I showed before. We're kind of intrigued by that, and we don't know exactly where this is going to go, but it may be a very powerful idea that is still just kind of working its way through the research community. Another one is the notion of large-scale language models. So things like GPT-3 and BERT, these are programs that are fed data about billions of words of off the internet, right? So mostly English language stuff, but you know, also programs, also stuff in other languages. And it just chews on all this data and it tries to predict future words from past words. And in the process learns a lot about language, like not just things like, well, there's nouns and verbs, which it definitely knows, but which kinds of nouns go with which kinds of verbs, and even little facts about the world, like what color is snow. Like it starts to learn about our world through this very indirect, just kind of reading everything that it can find online. And so that's a really big one. That's pretty exciting. And that one's already having a lot of impact. One that hasn't had a lot of impact yet, but is pretty exciting, is the notion of meta learning. So creating learning algorithms that can create learning algorithms, right? So they learn how to learn better. And we're not sure where that's going to go. It may just kind of be a little bit of a dead end, but it's definitely something that seems important, because one of the things that makes human learning so powerful is that we get better at learning as we learn more stuff. And we want programs to be like that, because you just can't learn quickly without that ability.
Thank you, Michael. And a related question is, what in your opinion, are the 3 greatest challenges resolving of which will make the next 3 greatest discoveries in machine learning?
All right. Okay. So 3 is a big number with these folks. So
let me see. At least one.
Yeah. So some of the things we focused on in the AI 100 report, one of them was there's a lot of concern now about this issue around algorithmic bias. So the notion that when we train algorithms using historical data, it sort of doesn't learn to solve the right problem. It learns to mimic historical accidents of the past, most of which are great, or maybe not even most of which. Like a lot of them are great, but a lot of them are really not great. And so how do we create machine learning algorithms that learn the right thing from the data that we actually have, which is, flawed? So that's one really big one. Well, I had another one. What was I thinking? Right. So that are going to enable the next 3 greatest discoveries. So I think, and we focused on this a lot in the report as well, I think I can make 3. I'll make 3. So I'll do a quickie second one. So number 2 is, how do we make machine learning algorithms that work better with people? So it's not just here's a lot of data, good luck to you. And then it comes back with a thing and we're like, is that what we wanted? And we have a sort of take it or leave it kind of attitude. Versus, systems that actually kind of work with us to produce answers instead of being so transactional, right? More interaction, less transaction. So that was number 2. Number 3 is a kind of related issue, which is how do we combine something more like symbolic reasoning, which is kind of the roots of the field of artificial intelligence and the way we think, with these kind of statistical processes that have been extremely successful in the last few years, especially with regard to kind of low-level sensor data. So you give it images or speech signals, right? Audio signals, or you give it kind of raw text, and having it be able to take this really low-level information and turn it into something actionable. That's been going great, but we don't really have a way of combining that with what we think of as more kind of high-level reasoning. So you give one of these systems like the text that says, my couch is pregnant, right? And it's fine. As far as it's concerned, that's just more text. But you could say that to a person and they'll be like, that's weird, right? That's strange. There's an attempt to try to make it make sense in terms of the world. And we think that might be a kind of symbolic process. Like we know what couches are, we know what pregnancy is, and we think that there may be a connection between them, and the connection isn't there. And so maybe we hypothesize something else. We actually originally in the report, we were going to write the chair is pregnant because we thought that was an example just like that. But then somebody pointed out, oh no, chairs can be people. Like the chair of a department is a person, and the chair, and a chair of a department can be a woman and can be pregnant, or it can be a reproductive person and actually be pregnant. So we make those kinds of connections. We read weird text and we try to make sense of it. And that's not what these programs do at this point. And that'll be a big challenge moving forward.
Thank you. Thank you, Michael. And actually the next question is related to this, your last comment. So you may want to elaborate. In particular, the question is about basically one of the hottest topics in economics or econometrics these days is about the causal inference. So the question is whether these advanced machine learning techniques may help more substantially in programming researchers' intent to computers. In other words, where they can explore the causality of phenomena and tell us that whether it is certain out of thousands or maybe millions of factors, which are the causes and which are just the confounding factors.
Yeah, so this is a great topic. I think causality is extremely important. And one of the things that I think is really interesting is it's gotten a lot more play lately. Like a lot of people are saying, maybe we should care about this. But that's still pretty recent in the field. We did end up kind of leaning into it a little bit in the AI 100 report because we do think it's an emerging and really important topic. But one of the things I think is really interesting is in the context of machine learning, there's, I mentioned 2 kinds of machine learning. So supervised learning and reinforcement learning. And the supervised learning people basically are saying, well, causality is impossible. We can't do anything about that. And the reinforcement learning people are saying, causality is trivial. It's already built into our models. So like neither group was really studying it because they either thought it was already part of their model or they thought that it can't possibly be in their model. And the reason for that is to distinguish causation from simply correlation, right? These things happen statistically together. You really need to be able to intervene. So you either need very carefully designed experiments that have the intervention information in them, or like in the reinforcement learning setting, you need the ability for the system to like try what if experiments, like let me do this thing and see what happens. And again, in supervised learning, it's just a big data set. So it can't do those kinds of interventions. And it is arguably impossible to really infer meaningful causal information from just that. But in reinforcement learning, it's what you learn is specifically, if I were to do this action, what would happen in exchange, right? What would happen in response to that? And so it learns a very, very explicit causal model of its actions' effects on the world. What we don't have at the moment is a reinforcement learner that learns about other kinds of causal effects in the world, right? Things that are not directly under its own control. And so the folks who are really trying to work out the mathematics of causality, hopefully will team up and create some new systems that do exactly what you're asking about.
Okay, thank you, Michael. Next question is also from econometricians. I remember from the student is, could you please explain or share some experience or rule of thumbs in choosing the machine learning algorithms? For example, how would you decide among the SVM, the random forest, the artificial neural networks, and other models in classification question, or some others? What are the rules of thumb that you use in practice, for example, in your work?
Yeah, this is a great question, especially in the context of my talk, where what I'm saying is, someday everybody should be able to train supervised learning algorithms to help them solve problems. And so at the moment, what does it mean? Well, what does the person have to do? You have to collect data, but that's not the end of it. You also have to choose the representation of the data, like how you have to clean the data, and you have to, at the end of the day, choose an algorithm to process that data to create a rule. And so support vector machines, SVMs, random forests, ANNs, which I'm guessing is artificial neural networks, are all different machine learning architectures, and they all kind of do different things. Like there's plenty of problems. You could apply all three of them and they'll all be fine. They'll all do the same thing. But there's also plenty of problems where the artificial neural network is great, but the other ones are terrible. And the random forest can be really helpful because sometimes they produce things that are maybe a little more explainable, but yeah, but then the artificial neural net is maybe good, but you can't make any sense out of what it produces. So this is a bit of an art at this point. I think that there's some high level rules of thumb that you probably already know, which is like, if you're dealing with low level sensor information, SVMs are not great. Random forests are not great. They really want their inputs to be something featureized, right? Something that says, for example, what is the person's income? And then it's represented as a number, as opposed to what is the person's income and it's represented as like a handwritten, like graphical image, right? If it's a handwritten graphical image, SVMs and random forests are going to be non-starters. But artificial neural nets are remarkably good at picking up, connecting low-level sensor information to these higher-level concepts. Support vector machines are, so if you do have a featureization, if you do have a representation of your data that is amenable to support vector machines, so that there's kind of higher level features and each data element is its values on all those different features, support vector machines are great because they can actually learn with a lot less data than you'd normally need for an artificial neural net. And I don't know, maybe random forests are sort of in between. I don't have as much hands-on experience with random forests, but the sorts of things that I've seen people use them for are analogous to SVMs. They're maybe a little more powerful than SVMs, but they're basically, the random forest idea is you're gonna learn a bunch of trees, right? That's why it's called a forest. You learn a bunch of different trees with different randomized starting conditions or maybe different subsets of the data, and you get a kind of like wisdom of the crowds effect, where each of the trees is kind of saying, I think it's this, but they all have slightly different pictures of how the world works. And somehow together they make a better group decision than any individual of them can make.
Okay, thank you. Thank you, Michael. So that was the question about the learning tool. The next question is also sent and was a particular remark that it's related to the question in your title about getting machines to do what we want. And of course, all of us, especially these days, they are, we're all faced by global challenges. And so the first thing we want is those global challenges to be solved, and we can't solve it. So we hope somebody else will solve it, right? So we were hoping the governments solve. They're trying, but maybe not so successfully. So now maybe it will be the machines that will be able to do it. So there is a list of few. I will list all of them, and you're welcome to choose some or all. It's up to you.
Yeah, sure thing.
So the first one is about the pandemics. How can machine learning help to mitigate or reduce the impact of future pandemics? And I understand that this is, you are much more precise specialist on certain things. You're not solving these problems, but you are one of the best experts, so your perspective would be very useful. Another is related is another very global thing is the global climate change, how machines can help there from your perspective. And of course, especially these days, especially in Australia, there is a lot of media articles about potential war and this and that. So maybe the machines can help there as well. Or many other questions that you think are global. If you can give your perspective, we would very appreciate.
Yeah, sure. I mean, I would love to be able to solve these problems right now. I 100% agree with you that these are very big deals. So let me start off by saying, first of all, people did try to use various kinds of artificial intelligence techniques to help with the current pandemic. And there was a kind of a summary report that was issued that indicated that it didn't really help very much, right? So the AI systems, even AI systems that were being developed to try to find patterns in data. I'm sorry for the dinging. I don't know how to make that stop. Find patterns in data and maybe suggest therapeutics, right, to make guesses about what kind of things are going to be helpful for treating people who have COVID. For reasoning about what the vaccines should be like. Like obviously, people were putting everything that they had, throwing into helping them try to make these decisions, and the evidence is it didn't really make it better. So there's a lot of possible reasons for that. Some of it is these algorithms are best when they have nice, clean data, and the COVID data was a huge mess. It wasn't internally consistent. It was coming from all sorts of different places. But the algorithms were just not up to the challenge at this point. Now, that being said, I wouldn't say that it was, the AI didn't help with the pandemic at all. It just kind of helped us get our daily lives to flow more easily. So as shipping issues became a problem, supply chain were breaking down. The only reason that they were able to come back online in spite of all the crazy changes that were happening all over the world is that people have computers and computer systems and AI that were helping them streamline that process. And so I think a lot of the ways in which AI and computing was helping during the pandemic were kind of infrastructure things, just keeping the world flowing and not so much curing the disease or treating the disease. Though in the future, they could help more with that, right? We're really just at the beginning of trying to understand how to analyze that kind of data by machine. And so it could really help in the future. It's just, there wasn't a lot of evidence that it helped this time. Climate change, we could blame the computers for this in part. It's certainly the case that these modern machine learning models that, for example, the GPT-3 that I mentioned before, that is able to process language in a really effective way by having read tons of text and other sources of information from the web, it uses a lot of energy. And so people have calculated that, that this was a significant, I think it was something like, multiple automobiles for a year kind of energy, usage or impact on the climate, which is, a couple automobiles is not that big a deal. There's a lot of automobiles already on the road. It's not great that we're adding to it, but I don't think it was a huge addition. But the fact of the matter is these systems are pretty resource intensive. And so that's not helping. Can they solve climate change? Well, climate change is really complicated. And I don't think we've been able to come up with the right way of looking at it. It's not the kind of thing where we can just feed in all the data and just have it kind of come up with a solution, because boy, we don't have the right kind of data. We don't have the right kind of information. Machine learning is definitely helping us build climate models, right? So the fact that we even understand at all what the impacts of various kinds of interventions are, that's supported by machine learning. That AI is definitely playing a role there, but it's not coming up with new ideas, right? And I think that's the right way to think about our relationship to these systems. And that's why I tried to emphasize the human component in my talk, is that I think they're not going to replace us, right? They're not going to come up with our ideas for us. But once we have our ideas and we want to actually act on them, we can delegate some of the more tedious aspects, some of the more, mindless or annoying aspects to the machines, and they can actually help us get it done. So if we can, as a community, as a world community, if we can come up with what we want to do and agree on it, the computers are going to be super helpful in actually getting it done. Global war. So global war, yeah. Well, so there's a lot of concern that AI is actually a destabilizer, right? So if a country can come up with really effective robot soldiers and just send them out there with no fear of loss of life on their own side, this could cause real problems in terms of people's willingness to go to war, right? So if it's if our people can't get hurt, yeah, we could just send the robots out to slaughter the others. That's a real problem. And there's scientists all over the world who've been trying to push back on this. It's actually a very complicated topic because it's potentially, it could save lives, right? To the extent that we're able to delegate some of this to machines, but it could also create, perverse incentives that are a real problem. And so my understanding is that world leaders are talking to each other about these things and thinking about the impact that AI has on security. And my hope is that, smart people will do the right thing and try to keep us safe.
Thank you, Michael. Thank you. That's also my hope. And in particular, it is also, I think, for all the scholars, scientists, it's also good to hear from the computer scientists that besides the artificial intelligence, we will continue to have the need for the real intelligence, at least in the near future, to harness that artificial intelligence and work for society, and keep us from the problems, and hopefully bring us to higher prosperity in the entire world. Thank you very much. It's been a great pleasure to have you with us to see this unique talk. And I recommend everyone from the audience to also go to the website of Professor Littman and then see a lot of interesting information, as well as Google Scholar platform, where you can see a lot of very interesting articles that were influential, written in the last few decades. And also, I recommend to watch the video. I watched the video when you were singing. In fact, you were singing twice, right? Back in those days, and then more recently there was some kind of meeting, and all of you four again got together and repeated that song, maybe even better. So, by the way, I'm wondering, so as I understood, this was not accidental that you were among those four to sing that in the first attachment. So, as I understood, you were behind creation of the entire idea protocols of the making attachments of this big size and so on. Can you maybe a little bit, since we have a little bit of more time, maybe you can
yeah, no, so just to set the record straight, no, the Nathaniel Bornstein, he actually was responsible for both coming up with the protocol, working on the team that developed that, and he wrote the lyrics to that song. He was the high tenor. I got to sing lead, so I got to actually sing the kind of melody line, which is great. But yeah, he's responsible. Even though he was singing backup, he's responsible for that effort. I got to do a couple cute little things, which is I integrated support for attachments to a couple mailers at the time. So I used Emacs as my mailer. It sounds silly now because now everybody uses web browsers as their mailer. But back then it made sense to have a text editor be your mailer. And I integrated MIME support into the Emacs mailer. But that was only because I just was nearby. They weren't counting on me to do it. It was something that I had access to. So yeah, no, sorry. I wish it were me. I was doing AI and cognitive science stuff even then, and Nathaniel was in this kind of internet, like he was doing internet. I was not.
Okay. Well, it was clear that you were probably the youngest on that team. At that time.
I was I was hired. So they were all like real official workers there. I was hired straight out of college to kind of support research in my group, and I learned a ton. And neural nets were big then, and then they stopped being big, and now they're big again. So it was really great to have been in a group where they were really trying to push the limits of neural nets at that time. Again, it's been a great sort of front row seat in watching the field develop.
Oh, that's nice. That's nice. But maybe since we touched at those times, maybe you can also give some advice to the current generation of people who are interested in machine learning. So your example shows that after college, you went not immediately to become a professor, but you first went to the industry. Maybe it's common in computer science, I don't know. It's less common in economics and econometrics and statistics. So can you give some advice to the career advice for younger listeners of this webinar?
Yeah, sure. As if they're computer scientists, I can try. If they're econometricians, I don't know. I don't know enough about your career paths, but general advice always is, stick with it. Try to find out what's going on and absorb it, right? So I guess some people give advice which is like, oh, try to get it ahead of the curve, like try to do things that no one's done before. And that's really hard as advice, right? Because you don't know how to do something that no one's done before. You don't even know what to pick. There's too many things to pick. So my technique, my strategy has always been, well, when people are doing exciting things, try to really understand it, right? Try to absorb it so that it's really just part of you. And you either will discover that it's hard to understand because there's a missing step in your head, in which case you need to learn something, or there's a missing step in the way they're explaining it, in which case you can kind of push on that and try to learn something new. But regardless, if you're not kind of where everybody else is, if you don't have it running in your own mind, it's really hard to contribute in a way that's going to be meaningful to people, right? Because at the end of the day, science is a social process, and it's about trying to understand the other members of your community and to really be a contributor to that community. And so that means really like being there for people and understanding what it is that they're bringing to the table.
That's very good. That's very good. I see that Tomohiro would like to ask some questions. Tomohiro, please.
Yeah. So thank you, Michael, for your interesting talk. So I have a couple of questions. The first question is because the audience are from government, businesses, and many organizations. In these organizations, one of the current main topics is how do we use AI, machine learning, data analytics to improve their performance. And from executive perspective, it's easy to say, can you do this job? Can you establish capability of AI for our organization? But however, one of the critical things is what can AI do? What cannot AI do? Distinguishing these two is a kind of one of the main issues these days. So for example, if the speed of changing environment is too fast, reinforcement learning may not be ideal because to catch up learning, the speed of change is much faster. And there are so many issues. And the critical point is, according to the current state of AI or machine learning, in business context or government, what AI can do, what AI cannot do to make this judgment. what kind of advice do you have for the audience, Michael?
Yeah, no, this is a really important question. I think both because people don't want to miss out, like people want to take advantage of these new ideas to try to make things better in their own neck of the woods. And I think that's great. But also because it's really hard. And so we devote a section of the report in the AI 100 to the question of using predictive models. So the thing that the machine learning systems are really the most valuable for these days is being able to make predictions. Like, will this, will there be flooding in this particular part of the world, or will there be, will this person default on their loan, or if we do this, if we adopt this project, is it likely to be profitable, right? So there's lots of kind of just questions about the future that you can ask. And what we devoted a section of the report to is, what do we know about better and worse ways of incorporating these kinds of predictive models into organizations? And the punchline is that it definitely should not be something where you kind of parachute it in from above, right? Where you just say, oh, wait, it's just this data. I'll just do machine learning on that data and we'll just apply that and it'll be great. Because almost every problem in the real world that involves people and organizations interacting is complicated. And if the machine learning system that's being constructed isn't constructed with the direct input of all the various stakeholders, it's going to be a disaster. It's going to be an organizational fiasco. And doing that doesn't guarantee success, but not doing that pretty much guarantees failure. So that was kind of the high order bit. That we didn't give specific technical advice on, oh, well, whatever you do, don't use a neural network. Like we weren't thinking at that level, but thinking at the level of the organization itself. It's really important that it be integrated, that it be developed in the context of the organization, and not something where it's like, oh, I've got a training algorithm, I can just train it on this data and now accept my answers, right? It's way more complicated than that. So I do think it's good, and I do think it's providing a lot of value to people, but the people who are getting the most out of it really take it the integration very seriously.
I see, I agree. So I want to ask a bit more about, because you mentioned about future predictive analytics. And what kind of context can we use enforcement learning or AI machine learning? Because the issue is because we need the data. And data is generated by something. If this structure that creates data changes, even we use data to learn something, the predictive may not be efficient or effective. And what's your opinion on this area? Typically, predictability of future.
On the predictability of the future, right? Like, what did they say that
AI.
Prediction is hard, especially about the future. So, I don't know. I mean, just sort of high-level guidelines that I can think of involve things like, you really want to have, so you were asking about reinforcement learning. So one of the things I think is interesting is that reinforcement learning has actually had kind of a minimal impact, except in the context of bandit algorithms. So bandit algorithms are a very narrow slice of reinforcement learning where the system is asked to make decisions that don't actually kind of impact the future. They really just affect the amount of success or the amount of reward that's coming. And reasoning about the future is really hard. And that's why I think partly we're seeing reinforcement learning algorithms that can do it are really being trained in simulators, right? They're not really being put into the real world because, first of all, it's hard. And second of all, to get good, it often involves millions and millions and millions of repetitions. So the algorithms that learn to play video games or learn to play Go, like they're playing the equivalent of 80 years worth of games, like morning to night, nonstop every day. And they learn a lot from that. But if it's a real world problem and not just a simulated, video game sort of scenario, well, then it's going to take you 80 years to experiment with the world and learn how to behave. And that's generally not supported, right? It's like you're making an investment that's not going to pay off for 80 years is a hard sell at this point, especially because there's going to be new ideas in the next 80 years that should make it a lot better. So I think reinforcement learning is still pretty limited in its ability to help in real world problems. Bandits are better.
Thank you. So you also mentioned about stakeholder engagement. It's critical to make AI work. I totally agree with you. And to start engage stakeholders within the organizations, any advice to managers, executives? What would be a starting point to embedded AI capability into the organizations? Any advice?
Yeah, so I don't have a lot of hands-on experience with that, but my like a common sensey kind of piece of advice would be the people who want to see it happen, the people who want to get the machine learning into the organization should really do their homework and learn about what kind of data is available, because by and large, if you don't have nice, clean, relevant data, these algorithms, even though they're remarkable, they can't squeeze water out of a stone, right? If valuable information isn't there for the harvesting, they can't make magic happen. So it is definitely the case that success depends on having a really good source of relevant data. And so if you're pitching it to somebody, show them what that data is and explain why you think that useful information is actually in that. Don't just think it's magic. Don't propose it as magic. It's like, oh, lots of people had, right? This is a terrible argument to make. Lots of people have had success with machine learning, therefore we should do it, right? The successes that you're seeing are carefully selected, right? There's way more people trying to get this to work than there are people successfully getting it to work. And if you want to be one of the people that successfully get it to work, you need to be like the people that have been successful. You can't just think that machine learning is the differentiator. It's really this synergy between the problem, the data that's available, and then the easy part is actually doing the machine learning.
Oh, yeah, thank you. So you mentioned about problem. Yeah, selecting problem is a kind of critical part in everywhere. And if I dig in a bit more, how do we pick up a problem? Because we have so many problems. If we have infinite amount of budget, time, human resource, we can touch many problems. What kind of problems should organizations pick? Any advice?
Yeah,
great.
I mean, the high level thing is, problems that have impact, right? Like if you should have some kind of reason to think that automating some piece of it or speeding up the process will actually affect your bottom line in some way, right? If you don't have that story, you're going to invest a lot of resources and it's not really going to change anything. The other thing that I think is an interesting rule of thumb that Andrew Ng popularized is the notion that often these networks, these machine learning systems, are best at making the same kinds of decisions that an expert could make given like a second of thought or 100 milliseconds of thought. This is the sort of thing like if I flash up a picture of a banana, you could name that it's a banana, right? That's the kind of systems that that seem to be best. They're not solving really deep, hard intellectual problems, except for in things like game playing where you can actually, you have a very crisp definition of the problem. You know exactly the rules of the game, so you can imagine ahead many moves in the game. Real world problems, even if they feel like chess problems or they feel like Go problems, they're super messy. They're super complicated, and you can't really reason very deeply about them. So Andrew Ng's kind of take on it is really nice, because what it's saying is if an expert who's really studied this problem for a long time would have to think hard, it's very unlikely that we can get a machine learning system to do it. If it's something that an expert can just kind of react to because the expert has just been exposed to so many examples, and there's like this gut feeling, I just go with that. Those actually seem to be quite amenable to machine learning training.
Thank you very much. I want to hand over Valentin. Thank you much.
Oh, you're muted.
You're muted.
Okay. Thank you very much, Tomohiro, for asking these very interesting questions, and thank you very much, Michael, for giving very interesting responses. to these questions and also to previous questions that I hopefully clarified to those who are asking. Are there any other maybe advice or any other thoughts you would like to share with us?
Yeah, I mean, don't forget you're a person. people can do really good things when they try. So don't turn over your judgment to machines. Like, make sure that they can explain themselves to you before you believe them. But otherwise, try to have a good future. Try to help make a good future. And it's a real privilege to get to talk to everybody. Thanks.
Okay, thank you very much. That's a very good note to finish. Again, thank you very much, Michael, for giving your wonderful presentation. And we hope that in the future we'll also have you. And hopefully when Australia opens up, we will have you in person. And
that would be delightful.
This task. Certainly, whenever I don't know when this will be. By the way, the Olympics, the 32. So not so far. We'll be in Brisbane, so where I am. So if you by that time we should open, I guess, at least for tourists. So if you want to come, then we would certainly like to host you, to show you around and so on. But hopefully, even before that, we will see you here or at other places.
I would love that. Thanks so much. It was great meeting you.
Thank you very much, Michael. Bye. Bye, everyone. Thank you very much for all the audience, for all the questions. And we look forward to see you in the future events. Thank you very much. Bye-bye.